a station model provides the reported weather conditions at the time the chart was produced. Let's take a closer look at each element of the model. The identifier is printed below and to the left of the symbol. LAF represents Lafayette, Indiana. The circle itself is shaded according to the amount of cloud cover that is present. Here, 3/4 of the circle is filled, indicating a broken cloud layer. A wind pointer indicates the true direction from which the wind is blowing. You can read the speed using the barbs at the end of the wind pointer. Each long barb represents 10 knots, while each short barb is 5 knots. In this example, the wind is out of the southeast at 15 knots. A pennant represents 50 knots of wind, while a circle around the station indicates a calm wind. When clouds are present, the level and type will be depicted in the station model. Low clouds are shown below the station model, with middle and high clouds printed above the symbol. You can find the decoding information for these symbols in various FAA publications and at flight service stations. To the left of the station circle is the temperature and dew point. If there is precipitation or weather obscuring the visibility, the appropriate symbol will be printed between the temperature and dew point figures. The symbol here represents intermittent snow. To the lower right of the station, the precipitation over the last 6 hours is recorded in hundredths of inches. The atmospheric pressure measured in tenths of millibars is shown in the top right corner. You must add the decimal and prefix the number with a 9 or 10, whichever brings the value closer to 1,000. The pressure at Lafayette is 1,018.7 millibars. Below this reading is the amount and tendency of any pressure change over the past 3 hours. At this station, the pressure has decreased 0.7 millibars. To ensure that you have the latest information, you should note the time of the observation. It is shown in a date-time box in the lower left portion of the chart. Then, by comparing the current surface analysis chart with earlier ones, you can get an indication of how the weather systems are progressing. Another graphic display of the weather is the weather depiction chart, which can be very useful in determining general weather conditions and the locations of low clouds and visibility. This chart, like the surface analysis chart, uses a station model to present the reported weather at various locations. However, this model has been simplified, making it easier to read. Cloud coverage is shown in the same manner, but the pressure information, wind, temperature, cloud types, and station identifier are not plotted. Below the station circle is the height of the ceiling or lowest cloud layer in hundreds of feet. This station model is showing overcast skies at 10,000 feet AGL. If the visibility is 5 statute miles or less, it is printed to the left. Weather or obstructions to visibility may also be shown. The visibility at this station is 3 miles in fog. Although pressure and wind information is not provided on these charts, areas of significant weather are outlined to help with route planning. Shaded areas indicate IFR conditions and contain ceilings less than 1,000 feet and/or visibilities less than 3 miles. Areas of marginal VFR weather with ceilings between 1 and 3,000 feet and/or visibilities between 3 and 5 miles are shown in solid lines with no shading. Finally, weather depiction charts also give the position of fronts. This frontal information, when added to the areas of IFR and marginal VFR weather, will give you a very good picture of the general weather affecting your route. The radar summary chart is another graphic display that is frequently used by pilots and briefers. It is used to identify large areas of precipitation and hazardous weather that could affect your flight. Radar summary charts are developed by using reflected radar energy or echoes of the precipitation areas. The more severe the precipitation, the stronger the echo. Each radar observation station is then combined into one hourly map. The strength of the echo returns is shown by solid lines surrounding shaded areas. The outermost line indicates precipitation that is light to moderate. A second line within the echo depicts heavy to very heavy precipitation, while a third line shows where intense to extreme precipitation exists. A solid single line shows a line of echoes with the boxed SLD indicating that the echo coverage is 0.8 or greater along the line. The direction of movement of an individual cell is indicated by an arrow. The speed, 45 knots, is shown at the point of the arrow. The letters NE indicate areas with no echoes, while the letters TRW stand for thunderstorms and rain showers. Echo tops are encoded in 2 or 3 digits. You will need to add 2 zeros to determine the actual altitude. For example, the top of this cell is at 34,000 feet, and the top of this one is 19,000 feet. Because it is assumed that all precipitation displayed on the chart reaches the surface, the chart does not include a symbol to show the base of the echoes. An area which is under a severe weather watch will be marked with a dashed box and an alphanumeric identifier. In this case, WS0006 identifies this as a severe thunderstorm watch area. When an area is marked with a WT, it is identified as a tornado watch area. When using a radar summary chart, remember that radar only detects areas of liquid or solid precipitation. It will not, for instance, show areas of fog, and the actual cloud tops may be higher or lower than the figures shown on the chart. The charts we have seen so far in this program have all depicted observed weather conditions. Other charts, including the Low-Level Significant Weather Prognostic, or PROG chart, offer a forecast of future weather. PROG charts are divided into 4 panels. The top 2 contain 12 and 24-hour forecasts of IFR and marginal VFR conditions, turbulence, and freezing levels. These 2 panels forecast the weather from the surface through approximately 24,000 feet. The bottom 2 panels forecast the location of pressure and frontal systems, as well as the areas and types of precipitation on the surface itself. Areas of IFR conditions, where ceilings are expected to be less than 1,000 feet and/or visibilities less than 3 miles, are enclosed by solid lines. Scalloped lines enclose marginal VFR areas where ceilings are expected to be 1,000 to 3,000 feet and/or visibilities are forecast to be between 3 and 5 statute miles. Areas which are forecast to have moderate or greater turbulence are enclosed by dash lines and contain symbols indicating the intensity and altitude of the turbulence. In this case, moderate turbulence can be expected from the surface to 3,000 feet over this area of the United States. The position of the freezing level at specified altitudes is also shown on the chart. A zigzag line is used to identify the freezing level at the surface. Freezing levels above mean sea level are indicated by dashed lines drawn at 4,000-foot intervals. On the lower panels, fronts and pressure centers are presented in the same manner as they are on surface analysis charts. In this example, this high has a barometric pressure of 1,022 millibars. Solid lines are used to denote areas of precipitation. Symbols are inserted to denote the type of activity expected. For example, 2 dots indicate rain, while 2 star symbols represent snow. A mixture of precipitation is indicated by showing 2 pertinent symbols separated by a slash. These symbols represent rain showers and thunderstorms. A bold dash line is used to separate precipitation with contrasting characteristics within an outlined area. For example, this dashed line separates an area of snow from an area of rain. Continuous precipitation is a dominant and widespread event and therefore is shaded. Intermittent precipitation is a periodic and patchy event and remains unshaded. Shading is also used to denote the amount of precipitation projected in a specified region. Areas with more than half coverage are shaded, and half or less coverage unshaded. The charts that have been presented in this program are but a few of the graphic weather products that are available for your use. As we have seen, charts of these types are very useful for obtaining a brief, general overlook of the existing and forecast weather along your intended route of flight and the surrounding areas. In previous segments, you learned how to interpret printed reports and forecasts as well as graphic weather products. But as a pilot, how does this information get into your hands? You can retrieve weather information from a wide variety of sources. Government facilities and private companies make weather reports and forecasts available by phone, television, fax, radio, and the internet. First, let's take a look at the sources of pre-flight weather information available to you. The most common source of pre-flight weather information is the Flight Service Station, or FSS. Flight service stations are FAA-operated facilities spanning the contiguous United States as well as Alaska and Hawaii. You may encounter the term Automated Flight Service Station, or AFSS. This term is sometimes used to differentiate the current FSSs that employ advanced technology from the former non-automated FSSs. An FSS typically offers a number of services, including pre-flight weather briefings, IFR and VFR flight plan processing, assistance for aircraft that are lost or in distress, and aid for search and rescue operations. Some flight service stations also have the ability to provide in-flight weather information in the form of En route Flight Advisory Service, or EFIS. If you happen to live in a city where an FSS is located, you can visit the station and receive pre-flight weather services in person if the briefers are able to handle your request at that time. Due to the limited number of stations in the U.S., however, a telephone briefing is a much more common means of receiving weather information. You can reach a flight service station on the ground by simply dialing a toll-free number anywhere in the U.S. When you dial 1-800-WXB-RIEF, you will be connected with the FSS nearest your location. The FSS phone system allows you to access a pre-flight weather briefer, along with other services such as FastFile, a flight plan filing tool. When you speak with a pre-flight briefer, you can request one of three types of weather briefings: an Outlook briefing, a standard briefing, and an abbreviated briefing. Before you can receive a briefing, however, you must provide some background information regarding your flight. This allows the briefer to tailor the weather information to your specific needs. An Outlook briefing is used when your departure is 6 or more hours away. This type of briefing is very useful for getting an overall picture of the general weather trends that may affect your flight. As your departure time nears, a standard briefing is necessary to obtain the most complete and in-depth weather data. A standard briefing is comprised of 12 separate and sometimes lengthy elements, so be prepared to write when you call. The briefer normally provides you with the following information: reported and forecast adverse weather conditions, information regarding whether or not VFR is recommended based on the current and forecast weather, an overall synopsis of weather systems, the current weather conditions, the en route weather forecast for your route of flight, the forecast for your destination airport, the winds and temperatures aloft forecast, NOTAMs, any air traffic control delays if applicable, a request for pilot reports, the availability of EFIS or FlightWatch, weather updates, and any other information you request, such as military activity along your flight route. Just prior to your departure, you may elect to check the weather one more time. An abbreviated briefing allows you to request one or two specific items and be advised of any changes in the weather since your last briefing. To expedite this briefing, be sure to include as much background information as possible, including the time and source of your last briefing. If you do not need to speak with a weather briefer, but you would like current weather information to aid in your pre-flight planning, some FSSs offer the Telephone Information Briefing Service System, or TIBS. You can access the TIBS recordings using the FSS 1-800 number. Typically, these recordings include route and/or area briefings for specific locations in the FSS region.
This recording prepared at 1408 Zulu. Briefing summary of current weather in eastern Colorado. Valid until 1500 Zulu. Summarize current conditions. A few clouds at 9,000 to 11,000 and high scattered cirrus. Visibility is unrestricted. Winds are generally northwesterly to northeasterly.
The TIBS system is recommended for preliminary briefings only and should not replace a standard weather briefing. If you have any questions about the recorded information, you can remain on the line to access a weather briefer. Be sure to provide the briefer with any background information in order to expedite the process. Another system you can use to receive complete weather briefings is the Direct User Access Terminal Service, or DUATS. DUATS is a free service that can be accessed on the Internet or with a modem and a 1-800 number. You can obtain all the items of a standard weather briefing through DUATS, as well as selected reports for specific locations. You can also file both VFR and IFR flight plans. DUATS, however, does not provide any details on military activities. You'll need to contact a flight service station for this information. You are required to have a current medical certificate to access the DUATS system. Further information regarding the DUATS service can be found in the Aeronautical Information Manual. In addition to DUATS, a number of organizations offer weather information by phone or on the Internet. While many of these sites and services are free, some require membership or specific user fees. Just one of many Internet sites providing weather information is the National Weather Service website, which is operated by NOAA, a weather service branch of the U.S. government. While websites are excellent sources of pre-flight weather data, the information presented may not be the most up-to-date and should not be used in place of a complete weather briefing from an FSS or the DUATS system. Jeppesen also provides several weather resources for pilots, such as JEPFAX, a worldwide weather fax service available for a small user fee. A complete listing of Jeppesen weather products, including JEPFAX, can be found at jeppesen.com or at flightneeds.com. Now that you've discovered where to obtain weather information prior to flight, let's explore how you can get updated weather information while airborne. One of the best sources of en route weather is En route Flight Advisory Service, or EFIS, also known as FlightWatch. This service is available from selected flight service stations. The frequency for FlightWatch is 122.0. After giving the EFIS specialist the details concerning your flight and your request, the briefer relays the latest weather information. You can also access weather data by monitoring selected VOR and NDB stations. These facilities normally provide local weather information updates or weather advisories. One such source of en route advisories is the Hazardous In-Flight Weather Advisory Service, or HIWAS, which is continuously broadcast over selected VORs. Information available through this system includes AirMets, SIGMETs, convective SIGMETs, summarized severe weather forecast alerts, center weather advisories, and urgent PIREPs. The NavAids and frequencies used for HIWAS can be found in the Airport Facility Directory. NavAids with HIWAS capabilities are also noted on aeronautical charts.
HIWAS for Miami Center area, recorded at 1845 Greenwich. Convective SIGMET 17 Echo. Between Key West and 50 nautical miles west of Vero Beach, Line of thunderstorms 25 nautical miles wide.
Other in-flight services which provide surface weather observations include the Automated Weather Observing System, or AWOS, and the Automated Surface Observing System, or ASOS. These systems record surface weather observations and automatically transmit real-time weather.
Denver Centennial Airport. Automated weather observation 2116 Zulu. Wind 040 at 12.
AWOS and ASOS broadcasts can be received up to 25 nautical miles from the station and up to a maximum altitude of 10,000 feet AGL. These stations are also accessible on the ground by phone. AWOS and ASOS facilities, frequencies, and phone numbers are listed in the Airport Facility Directory and the J-AID, as well as noted on aeronautical charts. As you have seen, there are numerous weather sources available for your use, and more methods to obtain accurate weather data continue to be developed. Additional information can be found in the FAR-AIM, advisory circulars, and other sources. You should always receive a pre-flight briefing before your departure. While en route, take advantage of EFIS and other en route information services to keep abreast of changes in the forecast weather. Fly safe by staying advised of current and expected weather conditions. With a wide selection of services available, obtaining the required weather data for your flight is both quick and easy.
When you look around the ramp at the variety of aircraft designs and sizes, it's obvious that airplanes are not all built for the same purpose, nor do they all perform the same. Regardless of the airplane you fly, it's your responsibility to know its limitations and be able to predict its performance. Some common questions that pilots ask when looking at an airplane are, how fast is it? How rapidly will it climb? How far will it go? And how high will it fly? Every airplane has its own unique performance capabilities and limitations. While one can fly extremely fast, another can take off and land on very short runways. It's not only important that you realize different airplanes have distinctive capabilities, it's also essential that you understand that an airplane's performance varies considerably under different flight conditions. Altitude is a primary item affecting performance. Specifically, as you gain altitude, the atmospheric pressure decreases. With a normally aspirated engine, the less dense air reduces engine power and overall airplane performance. It's essential that you consider this when operating at high-elevation airports. Air density also decreases as the temperature rises because air molecules expand as they are heated. Therefore, the performance of your airplane diminishes on hot days. Finally, if the humidity is high, the air entering the engine contains water vapor, which takes up space normally available for vaporized fuel. This moist air tends to retard even burning in the cylinders. One of the most effective ways to determine how your airplane will perform is by computing density altitude. Earlier, you learned that density altitude is pressure altitude corrected for non-standard temperatures, and that they equal one another only when standard conditions exist. Now let's look at an example of how density altitude is calculated and what this value actually means. Imagine that you will be departing an airport located at sea level. If standard atmospheric conditions exist, your airplane should perform as expected for sea level operations. Let's assume that the pressure altitude is the field elevation. However, the temperature is 40 degrees Celsius, or 25 degrees above standard. By using a chart or flight computer, you'll find that at 40 degrees Celsius, the density altitude is approximately 2,800 feet. This computed density altitude value means your airplane will perform as if it were departing an airport nearly 3,000 feet higher than the one where it's actually located. Because the density of the air is so much less with this above standard temperature, your airplane's performance will diminish. It's important to remember that the higher the density altitude, the lower the airplane performance. Remember that high altitudes, high temperatures, and high humidity all equal a high density altitude. Most modern performance charts have the density altitude computations built into them. But before we look at some of these performance charts, let's consider a few other factors which influence performance. You have learned that the air moving around the wings produces lift. Likewise, existing wind conditions have a big impact on airplane operations, specifically takeoff and landing performance. For example, headwinds are desirable for both takeoffs and landings. During the takeoff roll, a headwind supplies additional lift to the wings. This enables you to lift off earlier than during a no-wind condition. During a landing, the headwind reduces your ground speed as you approach the runway. This, in turn, shortens the landing roll. Aircraft performance can also be influenced by the runway itself. Many runways slope from one end to the other. You need to consider the gradient when determining takeoff and landing distances. For example, if you land uphill, the airplane will decelerate faster than normal, which will decrease the landing roll distance. On the other hand, departing uphill will lengthen the takeoff roll since it takes longer to accelerate to liftoff speed. The opposite conditions exist when the runway slopes down. Now your takeoff roll will decrease because you're able to accelerate faster. However, your landing roll will increase because it takes longer to slow down. You should also pay close attention to the effects of operating on runways with surfaces of snow, mud, water, or grass. The friction produced by these surfaces may significantly increase your takeoff roll. Now let's turn our attention to some examples of performance charts that you'll likely encounter during your flight planning. The most important source of information available for these calculations is the Pilot's Operating Handbook. However, the performance data from each POH applies only to a specific aircraft. Therefore, when you're determining the performance figures for a particular aircraft, make sure you're using the correct POH. Suppose you're going to be departing a short field and you want to know the ground roll and total distance required to clear a 50-foot obstacle. For this type of calculation, you'll need to refer to the takeoff distance chart. Before beginning, you need to note the conditions necessary to achieve the computed values on the chart. These include the flap setting, the power setting prior to brake release, the runway conditions, and the associated winds. Other notes are included for making adjustments for varying wind and runway conditions. For this example, let's assume the following conditions exist. The pressure altitude is 3,000 feet. The temperature is 20 degrees Celsius. And the airplane is at its maximum takeoff weight of 2,400 pounds. The table lists the appropriate airspeeds for liftoff as well as the recommended speed once you're 50 feet off the ground. These airspeeds help to assure that the airplane will perform as shown. First, locate the pressure altitude of 3,000 feet. And then move horizontally to the current temperature of 20 degrees Celsius. Under these conditions, the ground roll distance is 1,230 feet, and the distance required to clear a 50-foot obstacle is 2,295 feet. As you can see, this chart does not cover every temperature or pressure altitude possible. Therefore, it's often necessary to interpolate values between the given variables. Now let's examine a cruise performance chart for a Beechcraft Sierra. This type of chart is extremely useful for estimating the speed of your airplane, as well as the fuel consumption at various altitudes and power settings during cruising flight. For this problem, let's assume the following conditions exist. The propeller will be set to 2,400 RPMs. The airplane weighs 2,600 pounds. The pressure altitude is 2,000 feet, and the temperature is standard at this altitude. After verifying that you have the correct chart, start with the pressure altitude of 2,000 feet. Move horizontally until you reach the information for a standard day. Within this area, you'll find the manifold pressure you should use to achieve the desired results. In this case, it is 22.3 inches. The fuel flow at this power setting is 54 pounds, or 9 gallons per hour. And the true airspeed is 120 knots, or 138 miles per hour. Landing distance charts are also helpful planning tools. Although they vary somewhat, they're designed to enable you to determine how much runway is required to land the airplane safely. This is particularly important if your destination airport has a relatively short runway. The layout used in this particular chart provides precise landing information as long as you follow the specified conditions. For example, this chart is only valid during a power-off landing with the flaps set at 40 degrees. While some landing charts provide just the ground roll distance, this one is designed to show the total distance required to land over a 50-foot obstacle. For this sample problem, we'll assume the following conditions exist. The temperature is 30 degrees Celsius. The pressure altitude at the airport is 4,000 feet. The airplane's landing weight is 2,100 pounds. And you're landing into a 5-knot headwind. Now use these values to predict the landing distance by following a path through the graph. The first step is to locate the current temperature of 30 degrees. Next, proceed vertically to the 4,000-foot pressure altitude of the destination airport. Move horizontally to the weight reference line, and then move diagonally to the airplane's landing weight, which is 2,100 pounds. Continue horizontally to the no-wind reference line. Then move diagonally until you reach the current headwind of 5 knots. Now move straight across to read that the landing distance over a 50-foot barrier is approximately 1,080 feet. Because your airplane's performance can vary substantially, it's vital that you understand how changing conditions can alter its usefulness. As you gain knowledge of how density, altitude, surface winds, aircraft weight, and runway conditions affect the airplane, and learn to use performance charts properly, you can safely and accurately predict the capabilities as well as the limitations of your airplane.
There are many factors that affect the ability of an airplane to perform under certain conditions. One of these is proper loading of passengers, cargo, and fuel. In this section, you'll learn how to determine if your airplane is within the weight and balance limits which have been established by the manufacturer. Each airplane is designed to be operated at or below specified maximum weights and within a certain center of gravity range. As you learned earlier in the stability section, improper loading can adversely affect performance. In addition, all figures in the performance section of the POH are based on an airplane being loaded within the specified limits. Let's begin our discussion by looking at the various aircraft weights with which you should be familiar. The starting point for any calculation is the basic empty weight, which includes the airplane, optional equipment, unusable fuel, and full operating fluids, including oil.
Payload includes the weight of the passengers and any cargo or baggage. Useful load includes the payload and the weight of the flight crew and usable fuel. The sum of the basic empty weight and the useful load is called the ramp weight, which is the weight of the aircraft during ground operations.
You adjust ramp weight by subtracting the fuel to be used for engine start, taxi, and run-up to get takeoff weight. This weight should not exceed the maximum takeoff weight found in the POH or the weight and balance records. If your airplane is too heavy, it might have trouble getting off the ground. An airplane also has a maximum landing weight. This weight can be determined by subtracting any fuel used during the flight from the takeoff weight. The maximum landing weight can also be found in the airplane's POH. If you operate your airplane above this weight, the shock absorbed during landing may overstress the landing gear or damage the wing support structure. When you have determined that your loaded airplane will not exceed the maximum weight, you need to ensure that it is safely balanced. An airplane is in balance when its center of gravity, or CG, is located within the limits prescribed by the manufacturer. The CG is measured in inches aft of a reference datum, which is an imaginary vertical line set at some point along the longitudinal axis of your airplane. The datum can be set anywhere the manufacturer chooses. Some popular locations are a point ahead of the airplane, the firewall, or the leading edge of the wing. For this airplane, it is located at the nose. The center of gravity for every component is located in relation to this point. The longitudinal distance in inches from the datum is called the arm or station. Since the baggage area for this aircraft is located 142.8 inches aft of the datum, its arm is considered to be 142.8. If you multiply the weight of an object by its arm, you get its moment. For example, the weight of the suitcase is 25 pounds. Multiplying this weight by the arm results in a moment of 3,570 pound-inches. By adding all the moments together and then dividing by the total weight, you'll get the center of gravity for the loaded airplane. It's your responsibility as a pilot to make sure this CG is within limits. To help you accomplish this task, manufacturers use 3 basic methods. These include the computational, graph, and table methods. Let's first work a problem using the computational or mathematical method. Your first step is to find the basic empty weight and moment in the aircraft's weight and balance records. This figure includes the weights of all permanently attached items. Therefore, if any equipment is added or removed, the weight and balance records must be adjusted. For this problem, let's assume the basic empty weight is 1,500 pounds. This weight and its moment, along with its CG if given, is then transferred to a worksheet which contains 4 columns labeled as shown. You must then complete the weights and moments for the rest of the useful load. As a sample problem, assume you weigh 170 pounds and you're going to be carrying 2 passengers who each weigh 180 pounds. Since one of the passengers will be sitting in the co-pilot seat, you need to add your weight to that of the passenger. The result is 350 pounds. Since the arm for the pilot and front seat passenger is 80.5 inches aft of datum, the moment is 28,175 pound-inches. The moment for the rear seat passenger is 21,258 pound-inches. The next major item is fuel. Since you intend to carry the maximum amount of usable fuel, which is 48 gallons, and since each gallon of avgas weighs 6 pounds, the total fuel load weighs 288 pounds. This weight times the arm of 95 inches yields a moment of 27,360 pound-inches. The last item is the baggage, which in this problem weighs 60 pounds. Its moment is 8,568. If no more items are loaded on the airplane, the computational list is complete. Your next step is to add the weight and moment columns. In this example, the total weight of the loaded airplane is 2,378 pounds. And the moment is 214,211. You should then verify that the total weight is less than the maximum weight found in the POH or the weight and balance records. If not, you will have to make a choice of not carrying as much fuel, taking less baggage, or leaving some of the passengers behind. You can now determine the center of gravity for your airplane by dividing the total moment by the total weight. The CG with this loading is located 90.1 inches aft of the datum. To determine if the CG is within limits, refer to the airplane's center of gravity limits graph. In this example, the numbers on the right represent the airplane's weight, and the numbers on the top represent the CG location. Enter the graph on the right at the number that matches the total weight of the airplane, which in this case is 2,378 pounds. Then move to a point just right of the 90-inch aft CG location. Since this point falls within the approved CG envelope, your airplane is properly loaded. Some aircraft manufacturers use the graph method, which is a simplification of the computational method. It allows you to determine the moment of each item without having to multiply each weight by its arm. In this example, assume this airplane is carrying the same load as before. To find the moment for yourself and your front passenger, enter the graph from the left side at 350 pounds. Proceed horizontally to the pilot and front passenger line. Then drop straight down and read the moment divided by 1,000. In this case, it is 13.0. Enter this moment in the appropriate space in the worksheet. Then follow the same procedure to find the moments for the remaining items. Once you have all the items listed and totaled, you must compare the total moment with the total weight to determine if your airplane is within limits. Notice that with this type of graph, you don't have to do any calculations to determine the center of gravity. Another simplified method of determining moment is the table method. It requires only that you locate a given weight, then find the corresponding moment. Notice that the moments in this table must be multiplied by 100 to compensate for the reduction factor. Also, if a single weight exceeds the limit, you should use two lower weights which, when added together, equal the single weight. For example, you know that you and the front passenger weigh 350 pounds. Since the table only goes to 200 pounds, you'll need to find the moment for yourself and then add it to the moment for the front passenger. You then need to transfer the weights and moments to the weight and balance worksheet. Once you've finished totaling the weights and moments, you can use the moment limits versus weight table to determine if you're within limits. Here, you must find your loaded weight and then verify that the total moment is within the minimum and maximum limits. Weight and balance is a factor that should be considered on every flight. Taking the time to verify that your airplane is properly loaded will increase performance and help ensure that you have a safe flight.
In this program, we'll look at how to solve navigational problems using two different types of flight computers. First, we'll discuss the mechanical slide graphic, or CSG, computer. Then we'll cover the TechStar, which is an electronic flight computer. Because this program is only an introduction, you should study the operator's manual for the computer you've selected in order to become thoroughly familiar with it. If you have a computer handy, you might want to work the problems as we're going through the program. We'll pause periodically to allow you to complete the problem. If you're only interested in the TechStar computer, you can forward the tape to that part of the program. The CSG computer has two sides, the wind side and the calculator side, which can be used to solve a variety of problems including time, speed, distance, fuel consumption, true airspeed, density, altitude, and conversions. There are three scales on this side of the computer. The outer, or A scale, can represent distance, fuel, speed, or other units, depending on the problem you're solving. The middle, or B scale, may represent similar items, as well as time in minutes. The inner, or C scale, is simply a conversion of time in minutes to time in hours and minutes. The outer scale is fixed, while the inner two scales are printed on a single rotating disc. The numbers on the computer can be assigned different values depending on the problem. For example, the 60 can have a value of 0.6, 6, 60, 600, and so forth. By mentally estimating the approximate answer, you can place the decimal point in the proper position. The graduations between the numbers, however, are not always equal. For example, between the 80 and 90, there are 10 divisions, with each division representing 1 unit. The third line right of 80 could be 8.3, 83, or even 830. Between the 21 and 22, there are only 5 divisions. Here, each line represents 2 units, so the third line right of 21 could be 21.6, 216, and so forth. Most of the calculations on the computer are ratios or fractions. For example, when determining time, speed, distance problems, there are 3 variables: elapsed time, speed, which is usually ground speed, and distance. If you know any 2 of the variables, you can quickly solve for the third. The face of the computer shows you how to solve for the unknown value in these ratio problems. If your aircraft speed appears over the index, you will find distance on the A scale and time on the B and C scales. For example, assume you're planning to fly your airplane at 140 knots for a distance of 350 nautical miles. How long will your flight take? First, place the speed index under 14, which is 140 knots, when you mentally delete the 0. Then look under the 3.5, or the distance of 350 nautical miles, to find the time in minutes. In this case, it is 150 minutes. Notice that you have to add a 0 to the 15. 150 minutes can be quickly converted to 2 hours 30 minutes by referring to the C, or hour scale. You can also use the computer to find the distance flown in a given period of time. For instance, at a ground speed of 120 knots, how far will you travel in 2.5 hours? First, set the speed index under the ground speed of 120 knots. Then go to the C scale and locate 2.5 hours or 150 minutes on the B scale. Directly above this number on the distance scale is your answer, 300 nautical miles. You determine the ground speed of your aircraft in a similar manner. If you've traveled 349 miles in 2 hours and 15 minutes, what is your ground speed? First, locate the time for this flight. Since 2 hours and 15 minutes is not marked on the C scale, you should use the time in minutes, 135 on the B scale. For 349 miles, you'll have to estimate the distance from the line representing 345 and the one showing 350. Then you can read your ground speed directly above the speed index mark. In this case, it is 2.5 lines right of the 1.5. By placing the decimal in the correct position, you can determine the ground speed to be 155 knots. Fuel consumption problems are basically the same type of calculations, except that the index now points to the fuel rate, which in this case is gallons per hour. The outer scale shows the amount of fuel burned, while the inner scales still show time. Suppose in your flight planning you need to know how much fuel you will need if your destination is 3 hours away and your airplane burns 8 gallons of fuel per hour. Like the speed problem, set the index mark under the rate of 8 gallons per hour. Then find 3 hours on the inner scale, or 180 minutes on the middle scale. Read the fuel required, 24 gallons, directly above this time. Another type of fuel problem is to determine your endurance, or how much time you can stay aloft. Assume your airplane has 42 gallons of fuel on board, and it uses 11 gallons of fuel per hour. This time, set the index under 11, which is the rate per hour. Under the 42, read 229 minutes, or 3 hours 49 minutes on the inner scale. You can also use this side of the computer to determine true airspeed. However, to do this, you must know 3 things: calibrated airspeed, pressure altitude, and air temperature. While in the air, you can determine the temperature by referring to your outside air temperature gauge. For pre-flight planning purposes, you can get the forecast temperature for your planned altitude from the winds and temperatures aloft forecast. If you're unsure of the pressure altitude and you're in an airplane, you can determine it by setting the altimeter to 29.92 and reading the indication. Make sure you reset the altimeter back to the current reported setting when you're finished. Calibrated airspeed can be found by referring to the pilot's operating handbook. Once you've determined all the necessary variables, use the window marked for true airspeed and density altitude, and align the temperature in degrees Celsius over the pressure altitude. Then read the true airspeed on the A scale opposite the calibrated airspeed on the B scale. As a sample problem, suppose the pressure altitude is 5,000 feet, the temperature is 20 degrees Celsius, and your calibrated airspeed is 150 knots. Using the proper window, align +20 opposite the 5. Notice that the altitude scale is in thousands of feet and plus temperatures are to the left of 0. Next, find the calibrated airspeed of 150 knots on the B scale. Then read the true airspeed of 166 knots on the A scale. Density altitude can then be read directly from the center window. If the conditions remain the same as in the previous problem, the density altitude will be approximately 6,700 feet. The other window is used to compute true altitude. Instructions are listed near the window. The computer can also be used for conversions. For example, a temperature conversion scale is located at the bottom of the disk. For nautical statute mile conversions, 2 arrows at the top of the fixed scale give the proper relationship. These and many other conversions are covered in your owner's manual. The wind side of the computer is used to determine how the wind is affecting your airplane's ground track and speed. As you learned earlier, the moment an object becomes airborne, it is affected by the wind. If the object has no propulsion of its own, such as this balloon, it will float at the same speed and in the same direction as the wind. An airplane is also influenced by the wind. While it doesn't drift freely like the balloon, it is deflected from its intended flight path and its ground speed is affected. To illustrate, suppose a free balloon is released in a 15-knot west wind. At the same time, an airplane begins a flight due north at 100 knots. After 1 hour, the balloon will have drifted 15 nautical miles to the east. The airplane, flying northward, also will have drifted this same distance. In this situation, you should have pointed the nose of the aircraft to the west of the destination to compensate for the wind drift. The angle formed between your heading and the flight path is called the wind correction angle. The wind side of the computer helps you determine to what extent you'll have to fly into the wind. There are two parts to this side of the computer: a rotating azimuth and a sliding grid. Notice that the grid is printed on both sides. The high-speed side is used mainly for solving problems at jet speeds. There is also a statute and nautical mile scale, which can be used on sectional and WAC charts. The low-speed side of the scale is used for aircraft flying at lower speeds. It contains concentric arcs, which represent speed, and straight lines radiating from a central point, which represent degrees right or left of the center line. The rotating azimuth is graduated into 360 degrees. The center of the azimuth is a frosted transparent material, which can be marked on with a pencil. Directly in the center is a round circle known as the grommet. At the top, on the fixed portion of the computer, is a true index, which is used as a reference for plotting wind and course direction. The center line printed on the grid can represent any direction by just rotating the azimuth so the desired degrees are aligned under the index. At the top of the grid are easy-to-follow instructions on how to find ground speed and true heading. To determine how wind affects your airplane, you will need to know true airspeed, wind direction and speed, and true course, which is your intended flight path as measured from the true North Pole. The method for determining true course will be explained in the next section. Suppose that you've determined your true course to be 310 degrees. The predicted wind at your altitude is forecast to be 180 degrees at 16 knots, and your true airspeed is 120 knots. What heading will you have to fly to maintain your desired course, and what effect will the wind have on your ground speed? The first thing you must do is plot the predicted wind by rotating the azimuth until the wind direction is under the index. Next, slide the grid until the grommet is over one of the heavy speed arcs. In this example, let's use the 100-knot arc. Then count up from the grommet 16 knots and make a mark, which we'll call the wind dot, over the center line. The wind speed should always be plotted up from the grommet. Now rotate the azimuth until the true course of 310 degrees is under the true index. Then slide the grid until the wind dot is over the true airspeed of 120 knots. Your ground speed can now be read under the grommet. In this case, it is 129 knots. You can then determine the wind correction angle by counting the number of degrees the wind dot is located from the center line. In this case, each line represents 2 degrees, so the wind correction angle is 6 degrees left. Since the correction is to the left, you must subtract 6 degrees from the true course to obtain your true heading of 304 degrees. To verify that these figures are correct, you can visualize that the grommet represents your airplane and it's heading toward the index mark. Since the wind is behind and to your left, ground speed should be higher than true airspeed, and the true heading should be left of the true course. This concludes the coverage of the CSG computer. If you wish to learn how to operate a Techstar computer, let the tape continue. Otherwise, please forward to the next section on pilotage and dead reckoning. The Techstar electronic navigation computer is quick, accurate, simple to operate, and is designed to solve today's navigational problems. Like the different sides of a mechanical computer, the Techstar has various modes which you must use, depending on the type of problem you're solving. The time, speed, distance mode is used for determining, among other things, how far you can go, how long it will take to get there, and how much fuel you will need. The altitude airspeed mode can be used to determine density, altitude, and true airspeed. The wind mode is used to find your heading and ground speed. The weight and balance mode is used for determining gross weight, center of gravity, weight shifts, and percent of mean aerodynamic chord. The timer mode helps you compute departure, en route, and arrival times, convert different time formats, and acts as a time up or time down counter. To access the different modes after you've turned on the computer, simply press the Mode key. This displays the 5 areas. To go into any one of the modes, press the Line Parameter key. Let's begin with a Time Speed Distance, or TSD problem. Once you're in a mode, the Techstar computer indicates which mode you're in and displays the variables you'll need to solve a problem. Notice that on this menu, the variables needed to solve a fuel problem are also displayed. Most of the calculations done on the computer are ratios or fractions. For example, when calculating time, speed, or distance, there are 3 variables: elapsed time, speed, which is usually ground speed, and distance. If you know any 2 of the variables, you can quickly solve for the 3rd. Suppose in your pre-flight planning you want to find out how long it will take to fly 350 nautical miles if your airplane averages 140 knots. The first thing you must do is tell the computer which variable you want to solve for. In this example, you're solving for time. Now key in the distance of 350 nautical miles, which is displayed on the scratch pad at the bottom of the screen, and then transfer it to the appropriate parameter line. Next, enter the ground speed of 140 knots by keying in 140 and then pressing the ground speed parameter line key. If you had wanted to, you could have entered the ground speed before the distance. Known variables can be entered in any order. You are now ready to find the time by pressing the compute key labeled CMP. The answer is 2 hours, 30 minutes. Now suppose you've arrived at your destination and it only took you 2 hours and 20 minutes. What was your actual ground speed? The first thing you'll need to do is select speed as the variable you're solving for. Since the distance didn't change, enter it into the distance parameter line. Key in the time by pressing the 2, and then the colon key followed by 20. Next, press the time parameter line key. Now find the actual ground speed by pressing the compute key. Your actual speed over the ground was 150 knots. Fuel problems can also be solved in this mode. For example, after you landed, you had your plane refueled and found out you had used 21 gallons of fuel. What was your actual rate of fuel consumed per hour? You could solve this problem using the secondary compute function of this computer, which will be discussed later. But for now, let's go back to the main menu by pressing the Mode key. Then access the Time Speed Distance mode and select the flow rate by pressing the key next to FLO. Next, enter the time of 2 hours, 20 minutes. Enter the fuel used by keying in 21 gallons and transferring it to the fuel quantity parameter line, labeled F. To find the fuel rate per hour, press the compute key. The answer is 9 gallons per hour. Now let's go back to the screen where we solved for ground speed and see how this same problem can be solved using the secondary compute function. To determine fuel rate from this point, simply press the compute key a second time. This gets you to an extended output screen where additional parameters may be computed from the same variables. Then key in 21, which was the total fuel used, and transfer it to the fuel parameter line. Fuel flow can be determined by pressing the compute key again and then the flow parameter line key. The answer is the same, 9 gallons per hour. Use of the secondary compute function is further explained in the operator's manual. To determine true airspeed and density altitude, you must be in the altitude airspeed mode, which is indicated by an ALT-AS in the display. To determine true airspeed, you must know three things: calibrated airspeed, pressure altitude, and air temperature. Calibrated airspeed, which is indicated airspeed corrected for installation and instrument errors, can be found by referring to the airspeed calibration table in the pilot's operating handbook. While in the air, you can determine air temperature from the outside air temperature gauge. For pre-flight planning purposes, you can get the forecast temperature for your planned flight altitude from the winds and temperatures aloft forecast. The pressure altitude can be found, if you're in the airplane, by setting the altimeter to 29.92. However, when you've finished reading the indication, make sure you reset the altimeter back to the current reported setting. As a sample problem, let's determine true airspeed, or TAS. Assume the pressure altitude is 5,000 feet. The calibrated airspeed is 150 knots, and the temperature, which was determined from a winds and temperatures aloft forecast, is 20 degrees Celsius. First enter 5,000 feet into the pressure altitude parameter line, labeled PA. Next, enter the calibrated airspeed and the temperature. Since the temperature was determined from a forecast, we need to input the temperature into the true temperature parameter line. Had we obtained the temperature while in flight from the outside temperature gauge, this value would have been entered in the indicated temperature line. Notice that once you've entered a value into one of the OR variables, meaning the value can go into either line, dashes appear in the line next to the other variable. Now press the Compute key. The true airspeed, in this example, is 166 knots. Density altitude is also determined in this mode. If the conditions remain the same as they were in the last example, all you have to do is press the Compute key a second time. The answer is 6,712 feet. The wind mode of the computer is entered by pressing the Wind key. When you're in this mode, the word wind will appear at the top of the display. When an object leaves the ground, it is affected by the wind. If an object has no propulsion of its own, such as this balloon, it will drift in the same direction and at the same speed as the wind. An airplane is also influenced by the wind. While it doesn't drift freely like the balloon, it is deflected from its intended flight path and its ground speed is affected. To illustrate, suppose a free balloon is released in a 15-knot west wind. At the same time, an airplane begins a flight due north at 100 knots. After 1 hour, the balloon will have drifted 15 nautical miles to the east. The airplane, flying northward, will also have drifted this same amount. In this situation, you should have pointed the nose of the aircraft to the west of the destination to compensate for the wind drift. The angle formed between your heading and the flight path is called the wind correction angle. To determine how the wind is affecting your airplane, you need to know 3 items: true airspeed, wind direction and speed, and true course. True course is your intended flight path as measured from the true North Pole. How this course is determined will be covered in pilotage and dead reckoning. Suppose you've determined your true course is 310 degrees and the predicted wind at your proposed altitude is out of the south, or 180 degrees, at 16 knots. Your true airspeed is 120 knots. What heading must you maintain to fly your desired ground track? And what effect will the wind have on your ground speed? After verifying that you're in the wind mode, press the parameter line key representing the variable you want to solve for. In this case, it's heading. Now enter the true airspeed of 120 knots into the true airspeed parameter line. Next, enter the wind direction of 180 degrees into the wind direction parameter line, labeled WDR. The wind speed of 16 knots is entered next by keying in 16 and pressing the WSP line parameter key. The true course of 310